In the previous video, I outlined a certain technique of dealing with real integrals with the help of complex analysis. Before practicing it and generalizing it even further, let me pinpoint the crucial step in what we did. We managed to reduce the computation of the original integral to the relation of the loop integral surrounding the vicinity of the singularity of our function at point z equals I. And this way, the value of our original integral was entirely defined by the values of our integrand in the vicinity of this singularity. Now, if you think a little of what we did, we actually made an implicit Laurent expansion of our function near this pole and used it to simplify the computation of this loop integral. And that's the main reason why we studied so attentively the Laurent expansion for the whole previous week. And now time has come to introduce a central definition in our course. The residue of the function f of z at point z0, which is an isolated singularity, is called the coefficient c-1 of an associated Laurent expansion. So if we write down the corresponding expansion, then symbolically, the residue of f of z at point z equals z0 is equal to c-1. Now, before we state a residual theorem, let us introduce one more important concept, namely the concept of a meromorphic function. The function, which is analytic in all of D, with the exception of a set of points which are poles of this function, is called a function meromorphic on D. Now, the residual theorem concerns the integral of a meromorphic function over a closed, non-self-intersecting, positively oriented contour gamma. It states that this integral is equal to 2 pi I times the sum of the residues of this function inside this contour. Now let me remind you of what is the positive orientation of the contour with respect to some domain. We say that the contour circles around some domain in positive direction if this domain stays to the left as we move along this contour. For example, if we move along the circular contour in a counterclockwise direction, we may say that this contour is positively oriented with respect to the inner disk, which is inside this contour. But if we move along the same contour in the clockwise direction, we may say that the contour is positively oriented with respect to the exterior of this disk. Now, the proof of the residual theorem is pretty straightforward. But before addressing it, let us prove a very simple property. Let us consider the following integral. It's a closed contour integral along a circle standard at some point A of z minus a to the power of n dz, where n is an arbitrary positive or negative integer. And what I want to argue is that this integral is equal to 0 in all cases, with the only exception of n equals -1. And in the latter case, it's equal to 2 pi I. Well, to prove this elementary property, let us introduce a familiar to us already parameterization. Z equals a plus r times e to I phi, where r is the radius of the circle. Then dz equals r e to I phi I d phi. And let's plug in this parameterization in our integrand. So what we obtain is the integral over phi from, say, 0 to 2 pi, r to the power of n plus 1, e to the power of I n plus 1 phi, I d phi. And we see that the integrand is exponential. So the antiderivative would be also an exponential function, which is periodic. So when we integrate on a segment of 2 pi, the difference of antiderivatives will vanish due to the periodicity of the function, with the only exception of a single situation when n is equal to -1. Well, in this situation, the exponential in the integrand disappears, it is turned into unity, and in this case we simply integrate I d phi and obtain 2 pi I. So that completes our proof. And now back to the residual theorem. Well, suppose we have an arbitrary closed contour, gamma, path, say, in the counterclockwise direction. And let's position some singularities of our function inside this contour. The main consequence of Cauchy integral theorem tells us that we may deform the contour in an arbitrary manner without the integral changing its value, as long as this deformation doesn't cross the singularities. So what we do? We deform this contour into a combination of infinitesimal circles round each pole, connected by straight infinitely closed lines, forming a dumbbell-like shape. Well, first of all, let's address these linear infinitely closed segments of our contour. Well, each pair is passed in opposite directions, and due to the fact that they are infinitely close to each other, these integrals eventually cancel each other because the function is essentially the same on both parts of these linear segments and the directions are opposite. So this way, our original closed contour integral is reduced to a sum of the integrals round these infinitesimal circles round each singularity. But each of these infinitesimal integrals is very easy to compute. For example, let's consider the integral like around singularity a1. Since the contour is positioned in the neighborhood of the pole, our integrand can be represented by its Laurent expansion near this pole. So let's write it down. It's a sum from minus infinity to infinity Cn times z minus a1 to the power of n. Now once we start integrating each term of this sum, we'll immediately realize that all of these integrals cancel. We just proved it, with only one exception, of the term containing power -1, where this integral will give us 2 pi I. So the integral round the first infinitesimal circle will simply be equal to 2 pi I times the corresponding coefficient in front of this power, c -1. But this is nothing but the residue of this function at point a1. And of course we may repeat the same procedure for all the other poles, and necessarily we'll recover the statement of the theorem. Now let's think a little what this theorem tells us. The theorem effectively reduces the computation of an arbitrary complicated integral to the computation of the residues of the function inside a particular contour. But the computation of the residues requires only the skill of Laurent expansion. And as we saw earlier, the skill requires only the knowledge of algebra and some differential analysis like Taylor expansion. And this is the marvel of complex analysis. It turned the integration into essentially differential procedure, which is an exponentially easier task. So to see how this works in practice, let's study some simple example. Let's consider a function f of z equals 1 over z times z squared plus 1. And we'd like to compute the closed contour integral of this function along the following contours. Contour C1, contour C2, contour C3, and contour C4. Now let's have a closer look at the analytic structure of our function. Well, it has simple poles at point z equals 0 and z equals plus minus I. Now let's simplify this function just a little bit. So first of all, we decompose the fraction 1 over z squared plus 1 as 1 over z minus I minus 1 over z plus I multiplied by 1 over 2i. And then let's decompose the product of 1 over z times z minus I as 1 over z minus I minus 1 over z multiplied by 1 over I. And the same goes for the next product. We decompose it as 1 over z minus 1 over z plus I multiplied again by 1 over I. And combining similar terms, we obtain 1 over z minus 1/2 of 1 over z minus I and minus 1/2 of 1 over z plus I. And from this decomposition, we may read the residues of our function at points 0 and plus minus I. The residue at point 0 is equal to 1, while the residues at points plus minus I are equal to minus 1/2. Now let's use the residue theorem to compute the respective integrals. The integral over contour C1. Well, there are no poles inside this contour, so there are no residues, and the integral is equal to 0. Now the integral over contour C2 is equal to 2 pi I times the residue of our function. There is only one pole inside this contour, pole at point I, and the residue is equal to minus 1/2, and the integral is equal to minus pi I. Now the integral over contour C3. Now there are two residues inside, at point z equals 0 and at point z equals I. And the integral is equal to 2 pi I times the sum of these two residues, which is minus 1/2 plus 1. And we obtain pi I. And finally the integral over contour C4. which is equal to 2 pi I times the sum of all three residues, which is 1, minus 1/2, and minus 1/2, and we obtain 0. So this is how residue theorem works in most elementary examples. Well, in our next video, we'll introduce a slightly different technique of computing the closed contour integrals, not via the shrinking of the contour, but on the contrary, via expanding them. And we'll introduce an important concept of residue of the function at infinity.